from UFI in Rio, and we'll talk about multi-system equality from pairwise tests and logic.
Thank you. I'd like to start by thanking the organizers again. It's always a pleasure to be at IIP, and especially in a workshop on foundations. So my talk has this foundations theme to it, and it's a little bit different from what's announced in the book, okay? So this is based on some joint work with Daniel Brod, who is also at Universidade Federal Fluminense. And if I have time, I'll mention some experimental implementation of some of these ideas that we did with Fabio Sciarrino's group in Rome. So the idea is to discuss about equality between many systems if all you can do is to compare pairs of systems. So that's the general idea. So that's why I gave this title. So the first part of the talk is all about logic. Okay, there's no quantum mechanics in it. So it's like a mathematical discussion. So I'll start by looking at this function. Okay, it's a good example, and it's going to be useful. It's the end function. And here you have propositions A1 and A2, and this is the end of them. So this is the truth table for the end function. Everybody knows it. And what I'd like to remark on this is that there are some constraints imposed by logical coherence that appear if you look at this function. So we're thinking about a process that prepares or outputs events corresponding to these two propositions and events corresponding to the end of these propositions. So you have a probabilistic aspect to this. And you can think of any possible set of probabilities for the first event, for the first proposition, second proposition, for the joint, the end, as being a vector in probability space. Okay? So certainly this is a possible state of affairs for these variables. This is another one, this is another one, this is another one. And if you have a probabilistic process, you have to have a convex combination of these four rows here in this probability space, right? And if you look at the convex combinations of these rows, it makes a polytope, of course. It's this tetrahedron that's drawn here. And this tetrahedron, or any polytope, can be described in terms of facets. So here we have a description in terms of vertices. Each row is a vertex of this polytope. And you can compute the facets. And these are the facets for the polytope, where P12 is the probability of the joint, right? So what I mean by a logical coherence inequality is this inequality that appeared here. So this is saying that if you have these probabilistic events coming out, and you have the probability P1 of event A1 be true, and P2 of probability A2 be true, then the probability of the joint is bounded by this expression. Okay? So by logic. So this means you can't have, for example, an event A1 happen with probability 0.8, A2 happen with probability 0.8, and then this right-hand side will be 0.8, 0.8 minus 1, that's 0.6. You can't have this happening together with a joint with the probability which is smaller than 60%. Okay? Just because these are too high. And this inequality is describing this. Okay? It's logic. These inequalities, Bell-like inequalities, right, were described by George Boole a long time ago. And Itamar Pitovsky described how to use this convex picture to obtain them in general. So what we did was, it's all logic, nothing quantum yet, right? We looked at the similar inequality for here. Here's an inequality for the joint of two events in terms of the probability of each event. And we looked at the joint of m events. So you have the end of all these m different propositions. Okay? And it's not hard to work out that the generalization of this inequality here, when you have m events, is this inequality here. Okay? It's just saying that the probability of the joint of m propositions is lower bounded by this combination of probabilities of each single event. Here, the number of propositions appears. Okay? So this is a facet of the polytope that I described when you look not at just two events, but m events, and the end of all these events. Okay? So this is an exercise, and this inequality will be useful for us later. Okay? So this is a bound on the joint of m propositions. And this is all just logic. Now, what does this have to do with equality? I had equality in the title of my talk, right? Now I'm going to tell you what these propositions are. Okay? Each proposition is about the equality of two systems. So proposition A1, for example, in this example, is alpha 1, system alpha 1 is equal to system alpha 2. Is in the same state or is equal in some sense. And proposition A2 is that alpha 1 is equal to system alpha 3. Okay? So you can represent this kind of system of propositions using a graph like I did here, in which vertices are the systems themselves and the edges connecting two systems is an equality, a pairwise equality relation. Okay? So I gave this example, but you can do that with complicated graphs with as many vertices and edges as you like. So if you have any connected, so you have all the vertices that you decided to pick, which represent systems, you can make a connected graph. That means everybody's being compared to someone in the same graph. There's no isolated set of vertices, right? And if these propositions represent equality of two systems, of course, if the joint of all the equalities will mean that all systems are the same, because the graph is connected, right? So you're saying this is the same as this is the same as this, and everything is connected. Then the joint of all these propositions is that everybody's the same, everybody's equal. Okay? Because of transitivity of equality. And then we can apply the inequality that I just derived for the joint of m propositions, right? So the probability that all systems are equal is lower bounded by this expression, in which you have just probabilities of pairwise equalities appearing here. See? So I just adapted the inequality that I found for the joint of m propositions to the case when each proposition is this system is equal to this other one, right? So on the left here you have that all of them are the same because it's the joint of all pairwise equalities, and on the right here you have the expression from the bound that I obtained. Okay? Another thing that you can derive from this is this, because the probability that all systems are the same is a lower bound for the probability that any pair is the same, right? Because all of them being the same is a pair being the same and other equality conditions. So this is a lower bound for this, right? So this means this thing actually works as a lower bound. This expression works as a lower bound for the probability of pairwise equality. And these pairwise equalities, which are lower bounded by that expression, do not need to be in the graph. So in this example here, see? This expression has the equality relations in the graph that I draw. But this graph doesn't have this edge here between 2 and 3. But nevertheless, the probability that 2 and 3 are equal is bounded by the probabilities that are in the graph. Okay? So we can just have a look at... do you have questions? Yes? You can pick any situation you like, okay? So for example, we did an experiment in Fabio Sciarrino's group in which these comparisons are actually Hongo-Mandel experiments with 2 photons to decide what the overlap is between this state and this and that. So you picked those on purpose because you want to do 2 overlaps, measurements of 2 overlaps, and deduce something about the third that you didn't do. So it depends on what you want to do, okay? But you can certainly look at different graphs. Yes? No, not here. But it's an interesting question. I didn't. You can do this analysis for the coherence inequalities for any function, any Boolean function, right? You can just write all the propositions, list all possible values of them, together with the possible values of the Boolean function you picked. I only considered the end because I was inspired by this work started by looking at actually at 2 photon measurements, overlap measurements. So the end was a natural thing because the end of all of these pairwise equalities gives you something like genuine indistinguishability between all the photons. But it's interesting from a foundation's point of view to look at different functions as well. I haven't done it yet. This is, by the way, this is all work in progress, right? What we report in the preprint is an experimental test of some of these ideas. And some of these results are actually from last week. Okay? Any other questions at this point? This is a just end. Yes. Yeah. The question is, no. What I'm saying is the joint here is the joint of all the propositions. That is end of all propositions. And each proposition is equality of two guys. So if you make end of all of them, then everybody has to be the same. So the connection, I used and because of that. So just working out this example for this simple graph that I gave here, okay, to see what inequalities we get. So you just have 3 different systems, 2 propositions which are about the equality of these two guys and the equality of these two guys. And this is the inequality that we obtain, that the probability that the 3 guys are the same is the sum of these 2 probabilities minus 1. Okay? And because the probability that 2 and 3 are the same is lower bounded by the probability that the 3 are the same, you get also this inequality. And this inequality is interesting because it's saying, look, the probability that these 2 guys are the same, and you never measured them, you never compared them, but you can give a lower bound for this probability if you know the probability that these 2 guys are the same and these 2 guys are the same, and they are high enough, of course. Because if these 2 probabilities are low, then you won't get any non-trivial bound. So you have to have this sum adding up to more than 1 to guarantee to have a larger than 0 probability that the 2 guys are the same. The 2 that you never measured in your graph. Okay? And these inequalities, they seem kind of, I started with the polytope and Joule and so on, but you can derive these inequalities in other ways, and you can do that using the inclusion-exclusion principle. You can just draw the sets and look at the size of the intersections and count the size, and you can find this inequality for 3. For more is a bit more complicated. Actually, it's much easier to do as I did. 4 or more. Okay, so up to now, we're just discussing about logic, okay? If you know that 2 objects are the same with this probability, and this other pair of objects is the same with this probability, you can deduce that this other pair has to be the same, at least with this value, with this probability, right? What happens when you look at quantum states? So you can ask, what plays the role of the probability that state psi and phi are the same, right? Being the same means yielding all results of any possible experiment that you do, which are the same, right? And the answer to this question is given by quantum mechanics by the overlap between the 2 wave functions. Because this is the probability that state psi will pass for a state phi in the most stringent test that you can do for state phi, which is a projection onto phi. Right? And this is the probability that state psi will pass on this test. And actually, even because of the projection postulate, if it passes the test, from then on, it's going to behave exactly like the state that you were testing. Right? So I'll make this association between the probability that 2 systems are the same to the overlap between the wave functions. Okay? So quantum mechanics tells us how to compute this probability that 2 systems are the same. And this overlap can be measured in a very simple setup, in a very simple circuit. This is the swap test. I don't know if many of you must have seen this before. You have 2 unknown states. You have an ancilla. You do a Hadamard, do a control swap, do a Hadamard, and measure the ancilla. The probability that you get 0 again, as it was in the beginning, is given by this expression in which you can read directly the overlap. So this is a way of computing the overlap without knowing what phi and psi are. You just have access to some physical states in state phi and some in state psi, because you have to run this a few times to get an estimate of the overlap. Okay? So this is, let's say, this would be the nice little circuit that you do to answer the question, with what probability are these 2 quantum states the same? You run the circuit a few times with some copies of these guys and estimate the overlap there. Okay? What about when you have more than 2 states? Quantum mechanics gave a very simple answer to the question, what's the probability that 2 guys are the same? But it doesn't give you as nice an answer for the probability of 3 guys being the same or more, right? So I'll start with this question. Suppose you're given the overlaps between 1 and 2 and 1 and 3, which are the black edges here. So sometimes tells you, look, there are these 3 states, and you can do the swap test between these guys, and you get these numbers for the overlaps. Can I guarantee that the overlap that I didn't measure is larger than 0? Okay? So what you're concerned with, you would like to do measurements on only 2 pairs of systems and infer something about the third that you never measured. You would like to prove that this other pair is non-orthogonal without ever directly measuring it. Okay? And the answer is yes, sometimes you can do that. Okay? And the proof is very simple. So you just assume that these 2 states here have 0 overlap. Okay? If they have 0 overlap, you can project alpha 1 into these 2 states, and the probabilities, these amplitudes with which you project onto alpha 2 or alpha 3, the probabilities associated with them have to be smaller than or equal to 1 because they are orthogonal, right? So the sum of these 2 probabilities is actually the probability that onto the subspace spanned by alpha 2 and alpha 3, right? So you start with this assumption that they are orthogonal, and you find that these 2 probabilities must add up to at most 1. Of course, if you measure these 2 probabilities with these swap tests, and you find a sum which is larger than 1, then you will have deduced that this must have been wrong, and actually the overlap is larger than 0. Okay? So this is a quantum mechanical proof that if the 2 probabilities are high enough, that the overlap of the other 2 has to be larger than 0. Right? And if we look at this condition here, remember, this is exactly the condition that we got for that simple example of 3 systems. This expression here is larger than 0 is exactly the logical condition for non-zero probability of the 3 systems being the same. If this is true, if this is larger than 0, that means all the systems, the probability that all systems are the same is larger than 0. Therefore, the probability of 2 of them being the same also has to be larger than 0 because it's lower bounded by the probability that the 3 are the same. Okay? So I did not use quantum mechanics for the logical part of the talk, but we obtained an inequality that gives you the probability that 3 systems are the same. And when this probability is larger than 0, in quantum mechanics we found that this guarantees that the third overlap is larger than 0 too. Okay? So this is the connection between this simple proof in quantum mechanics with the previous proof, which was a logical proof. So you can say that measuring these overlaps here and computing classically what the probability is for the 3 systems being the same gives you a witness that the overlaps that you didn't measure have to be larger than 0. Okay? You can generalize this to many systems. It's easy. The proof is very simple. So for example, you could have a look at, for a star graph like this, you have system 1 being kind of a reference system, and you do measurements of overlaps between 1 and 2, 1 and 3, 1 and 4, and 1 and 5. If the sum of them violate that inequality that I have, then you know that system 2 and 3, 2 and 4, 2 and 5, 4 and 5, 3 and 4, all have to have a larger than 0 overlap. And you never measured it, you see? It's just because of that simple proof, the generalization of that simple proof to any number of states. So you measure some overlaps. If they're high enough, you know that the others have to be non-zero. Now, an interesting thing is that quantum mechanics violates the logical inequality. So what do I mean? Here, I was just saying, look, if this is larger than 0, then the overlap will be larger than 0. But I didn't say anything about how much the violation of this implies for this. The classical inequality actually said how much. It said precisely, look, this probability of the joint is lower bounded by this expression. And actually, it is this expression, right? The difference between the expression and 0. So when you look at what happens in quantum mechanics here, you see that quantum theory violates this logical inequality, which is an interesting and very curious thing. So let's have a look at a very simple example. Again, just the three systems that I mentioned. So you have 3 systems, and you have this inequality from logic, okay? The probability that B equals C has to be lower bounded by this sum of 2 probabilities minus 1. Okay? Now, we made this association between probabilities of two systems being the same with the overlaps. That means we should expect from classical logic, okay, classical reasoning tells you that you should expect this to be true, okay? Because if this is probability that A passes for B is equal to B, this is probability that A is equal to C, this expression should be a lower bound for this quantity, which is a probability that B is equal to C, right? But for these states here, which are the states that maximize this violation, okay, you have three states on a great circle in the block sphere, forming exactly the simple triangle here, okay? And these states have the property that the overlap between A and B and A and C is very large, 3/4. While the overlap between B and C is very small, it's just 1/4. And if you plug this in here, you get here, for this expression, which should be a lower bound to this, you get a half. And for this overlap, you get 1/4. Certainly, of course. 1/4 is smaller than a half. It's not larger than a half. You see? So what I'm saying is quantum mechanics is violating what you expect from classical logic. Okay? Because if these two systems are so alike, and these two systems are so alike, classical theory would say that these two systems had to be equal, at least with probability half. And quantum mechanics is telling you that they are equal with just probability 1/4. Okay? So this is the quantum mechanical violation of our classical expectation in this comparison game. Okay? And of course, it's interesting to think about what's the meaning of this violation, whether this can be a resource, whether this is connected to contextuality. This is very recent. I haven't had time to think through all of this, but if you guys are interested and have ideas, I'll be happy to discuss with you. So now I'd like to mention, in the few minutes I still have, about some experiments that were done using these ideas. Okay? So first, the experiments were done in a quantum optics lab, and what we did was we would like to do something similar to a swap test. And when you look at quantum optics, you see that a simple 50-50 beam splitter, the Hongo-Mandel test in a simple 50-50 beam splitter, plays the exact role of this guy. Because what this circuit does is to project onto the symmetric subspace of these two systems. That is, it checks whether when you exchange the systems, things are the same or not. Okay? So this is what the swap test is doing. And when you look at what happens with the Hongo-Mandel test, you put one photon here, one photon here. The probability of bunching, that's the probability that the two photons come out together, either here or here, is exactly given by this expression in which A, B are the spectral functions for the two photons that you put in. So the Hongo-Mandel is a very natural thing. It's linear optics. There's no feed forward. It's very simple to do. And it gives you exactly a measurement over the overlap of the wave functions describing the two photons. Okay? So that's good. It's a very convenient thing to do. So what we looked at this paper was we would like to do tests that guarantee that no two photons are orthogonal to each other. Why? Because we want to have sources that produce identical photons for metrology, for boson sampling, for whatever use you have. And of course, suppose you have a source that produces n photons, and you would like to say, look, all these photons are indistinguishable. I was careful to make them indistinguishable as much as I can, right? How can you do that in a lab? Of course, you can do Hongo-Mandel tests between all pairs of photons. But if you have n photons, then you have this number of pairs. So this is the number of Hongo-Mandel tests you would have to do to guarantee everybody is orthogonal to everybody. Okay? But instead of doing that, you can use our reasoning and do a test of just a linear number of Hongo-Mandel tests. If they give you very high overlaps, we can use our proof there to guarantee that the overlaps that you never measured, all the other ones, other n-squared overlaps, will be non-zero. You see? So this is kind of works a bit like a witness of genuine multi-photon indistinguishability. You measure a few, you deduce that the unmeasured ones have to be non-zero using quantum mechanics. So this is a practical kind of application of what I'm describing, and that was described in this paper here. Okay. So I get to the end of the talk. I just want to a bit what I discussed. We looked at comparison between systems, right? And in quantum mechanics, you can compare two systems using the swap test. It gives you an estimate of the two-wave function overlap. If you want to compare more than two systems, then I showed you a way of doing that using just n-1 tests of two systems. And if these overlaps are high enough, then you can guarantee that there's a non-zero probability that all these systems are the same. That there are no pair that's orthogonal, that is completely distinguishable. And at the end, we saw that quantum mechanics violate these logical coherence inequalities for the equality of systems. And this is an intriguing thing. It's a very simple thing, right? Very, very simple. And I'd like to understand this better. And if you guys have seen something like this before, please talk to me. I'm curious about that. Of course, I would like to know whether this violation is related to contextuality, to an extendable product basis, or what, right? I haven't really thought about it. And I would like to know whether the amount of violation of that simple inequality that I gave you and the generalization to n parties and particles, maybe this amount of violation can be proven to be a resource for some quantum information task that you can do relying on indistinguishability of the photons, right? So this is what I had to say. I'm open to questions. Thank you for your attention.
Well, this is probably more semantic than